All right, so lesson 5D is really going to focus a lot on the graphs of an original function and how it's related to the graph of its derivative. And even to the graph of its second derivative a little bit, but we're really going to focus a lot on the original graph and the first derivative. So just some things to keep in mind. The first derivative f prime of a function f gives the slope of f at any x value. So if f prime is greater than 0, the slopes are positive on f, and f will be increasing. If the first derivative is less than 0, the slopes of f are negative, and f will be decreasing. The second derivative f double prime gives the rate of change of the slopes, or the concavity of f. If f double prime is greater than 0, the slopes of f are going to be increasing, so the graph is going to be concave up. If f double prime is less than 0, the slopes of f are going to be decreasing, and f will be concave down. So those are just some things to keep in mind as we're looking at the relationship between the first derivative, the second derivative, and the original graph. So here we're going to go ahead and look at an example. We have the graph of the derivative is shown to the right, and it is known that f of 0 equals 0. Okay, so right here, we know that on the original graph, f of 0 is going to equal 0. And then we're trying to figure out which of the following could be the graph of the original function. So all of the ones that are answer choices do have f of 0 equal to 0. So that's not going to rule any of them out for us. But let's look at some things that are on the derivative that can help us identify some places on the original graph. So when I'm looking at the derivative, I have the derivative is 0 here, and also the derivative is 0 here. And even here at the beginning, right here, the derivative is going to be 0. Now, when the derivative is 0, the original function is going to have some sort of horizontal tangent line at that particular point. Now, that's leaning me more towards one particular answer, but I want to kind of hold off on that and talk about the positives and negatives. So here from 0 to 2, the first derivative is positive, and from 3 to 4, the first derivative is positive. Oh, I missed one of the zeros as well. Oops. So it's also going to have a horizontal tangent at 3. I missed that one. So we have 4 places actually where we're going to have horizontal tangent lines. So it's positive from 0 to 2, which means the graph is going to be increasing from 0 to 2. And it's going to be positive from 3 to 4, which means the graph's going to be increasing from 3 to 4. And then it's going to be negative from 2 to 3, which means the graph is going to be decreasing from 2 to 3. So let's go ahead and just kind of look at each of these and see if there's any we can rule out on that fact. So the graph has a positive slope from 0 to 2. Now, if I look at the first one, it has a positive slope right here, and then it turns negative, and then it turns back positive. So this one has a lot of different increasing and decreasing parts between 0 and 2. And we know that our graph should only be increasing from 0 to 2 because that's where the first derivative is going to be positive. Now, in B, we go up from 0 to 1, and then we come down from 0 to 2. So that one's not completely increasing all the way from 0 to 2 either. Now, this one does increase from 0 to 2, and so does C. C increases from 0 to 2. So we have C and D still in the running. We're going to rule A and B out. Now, from 2 to 3, the graph's supposed to be decreasing. If we look at 2 to 3 here, the graph is decreasing very, very little, but it still is. And from here, 2 to 3, the graph is decreasing. It actually decreases a lot. And then from 3 to 4 on both of these graphs, we're back increasing. So 3 to 4, we're increasing. Now, let's go ahead and look at our critical points here, the places where the first derivative is equal to 0. So when f prime of x is equal to 0, we're going to have a horizontal tangent on the original graph. Okay, so even if I just look at 2, 2 on graph C would have a horizontal tangent there. 2 on graph D, it's kind of weird at 2, honestly. It looks like it's, maybe but it honestly looks like we have kind of like a corner situation happening. So I really wouldn't call that a horizontal tangent there. So I'm going to go with a no on that one. But we can also like look at 0 also. And at 0 for this one, we wouldn't have a horizontal tangent either. We would have a tangent that line is a positive slope. But here on graph C, we would have a horizontal tangent at 0. We have a horizontal tangent at 2. We would also have a horizontal tangent at 3. And then even if you look at 4, it's going back flat at 4. So the graph that fits best with this first derivative is going to be graph C. All the rest of them don't fit up well with the horizontal tangents and the increasing and decreasing pieces. All right, so for example 2, it says for a function f of x, it is known that f prime of x is greater than 0 and f double prime of x is less than 0 for all x. Which of the following could be a table of values for f of x? So let's first pay attention to that f prime of 0 or f prime of x is greater than 0. That means the first derivative is positive, which means f of x is going to be increasing. Okay, so we can go ahead and probably rule some problems out just on that fact. So A is increasing, so we can't rule A out. B is kind of all over the place. It goes down and then up and then down and then up. So B we can go ahead and cross out. C, negative 12 to negative 10, negative 10 to negative 5, 5 to 3, and 3 to 13. That one is increasing. And D, negative 15 to negative 5, negative 5 to 2, 2 to 6, and 6 to 7. That one is also increasing. So we were only able to rule out B for the first little piece of information. Now, it says the second derivative is less than 0. Now, what that means is that it's going to be concave down. We really can't see concavity in a table. But it does mean that the rate at which it's increasing is slowing down. So it keeps increasing, but as we go up in x values, the change is changing slower, essentially. So the slope increases more slowly as x increases. So let's look at the change. So essentially the change is slowing down. Still increasing, but it's increasing less slowly as you go up in the table. So here we have a change of 2. Here we have a change of 3. Here we have a change of 7. And here we have a change in 3. So it is not increasing less slowly. So it's actually increasing faster, but then it does slow down. So it's not going to be A. In C, we go from negative 12 to negative 10. So so it goes up 2. Negative 10 to negative 5, so up 5. Negative 5 to 3, so up 8. And 3 to 13 is going to be up 10. So that one's actually increasing faster as you go down. So that one's not going to be it. If it said that f double prime was greater than 0, that one would be an option. Then we go from negative 15 to negative 5, so that's up 10. Negative 5 to 2 is going to be up 7. Then we're going to be up 4. And then we're going to be up 1. So here's the one that's going to fit the criteria the best, because it is increasing the whole time, but as x increases, the slope is increasing more slowly. Okay, so the increase is slowing down as we move up the graph, which means it's going to be concave down. So it increases faster, and then it starts to slow down, which means the graph is concave down. So that's going to be D. All right, so example 3, it says, using the figure below, complete the chart by indicating whether each value is positive, negative, or 0 at the indicated points. For these problems, if the point appears to be a max or a min, assume it is. If it appears to be a point of inflection, assume it is. All right, so let's look at point A. Point A, f of x is negative because it's below the x-axis. It's on an increasing portion of the graph, so the first derivative is going to be positive. And then if you look at that piece of the graph, this piece of the graph is concave down, which means the second derivative is going to be negative. All right, B. B is above the x-axis, so f of x is going to be positive. It's also on an increase in portion. It's getting close to where it would be 0, but it's still increasing right now. And it's still on that concave down portion, so that is going to be negative. All right, now C. C is in a positive portion of the graph. It's on a part of the graph that's decreasing, so the first derivative is going to be negative. Now, the second derivative, it looks like it's concave down before, and it looks like it's concave up after. So I'm going to say that that is a point of inflection, so the second derivative would actually be 0. Now let's look at point D. Point D is on the x-axis, so the value of f of x there is going to be 0. It's also at a minimum, so the first derivative is also going to be 0. And then it's not a point of inflection. It's on a portion of the graph that's concave up, so the second derivative is going to be positive. Now E. E is on a positive piece of f of x. It's on an increasing piece of f of x. And then it looks like it's concave up before and concave down after. So I would actually call E a point of inflection, which means the second derivative would be 0 there. All right, F. It's on a positive part of f of x. It's above the x-axis. It looks like it's at a maximum. So the first derivative would be 0. And then it looks like it's concave down. So the second derivative would be negative. Now G. G looks like it was positive. It's on a decreasing part of the graph. So the first derivative is going to be negative. And then I'm not sure, it doesn't necessarily look like it's a point of inflection. I feel like the place where the concavity changes would be closer to like right here. So I'm going to say it's still on the concave down portion of the graph. So it's going to be negative there. It looks like it doesn't change from being concave down to concave up until you get a little bit closer to H on the line there. All right, H. H is negative. Okay. It also looks like it's at a minimum value. So f prime of x is going to be 0. And then here it's concave up. So it's going to be positive. I is on a negative part of the graph. It's also on an increasing part of the graph. So the first derivative is going to be positive. And then it is on a portion that is concave up. So that second derivative is also going to be positive. Now J. J is the x-intercept, so f of x is going to be 0. It's on an increasing part of the graph, so the first derivative is going to be positive. And then it looks like it's still on that concave up portion, so that second derivative is also going to be positive. So that's kind of how you would analyze the graph and analyze the sign of the first derivative and the second derivative. The first derivative is all about whether it's increasing, decreasing, or a max or a min. If it's increasing, the first derivative is positive. If it's on a decreasing portion of the graph, the first derivative is negative. And if it's on a max or a min, the first derivative is going to be 0. When you're looking at the second derivative, you're looking at concavity. So if it's concave down, it's going to be negative. If it's concave up, it's going to be positive. And if it's a place where the concavity changes from down to up or up to down, it's going to be a point of inflection. So the second derivative is going to be 0 at those particular places. All right, so let's go ahead and look at example 4. The graph of the function f is shown in the figure to the right. For which of the following values of x is f prime of x negative and decreasing? All right, so let's think about what that means. F prime of x is going to be negative when f of x is decreasing. And then f prime of x is going to be decreasing when f of x is concave down. Because when the first derivative is decreasing, that means the second derivative is going to be negative. And when the second derivative is negative, the original graph is concave down. So let's go ahead and think of where f of x is decreasing and where f of x is concave down. We're looking for both of those things to be happening. I'm really trying to switch to the eraser here. It doesn't want me to. Okay. So first, let's pay attention to where f of x is decreasing. Oh my goodness, it will not switch to the highlighter. Okay, so let's pay attention to where f of x is decreasing. So f of x is decreasing here. F of x is also decreasing here. So those are the two places where the first derivative is going to be negative. So we're already ruling out C and E. So we're either A, technically not even B. B, technically the first derivative doesn't exist there because it's a cusp. So really we're down to A or D. So I can go ahead and rule out B, C, and E. Now, for both of these, we're going to be looking for when the second derivative is less than 0, which means it's where the graph is going to be concave down. So the graph is concave down at A. At D, the graph actually is changing from being concave down to concave up. So D is actually a point of inflection, which means at D, the second derivative would actually be equal to 0. So that's not going to be the case. So the one that fits the criteria is going to be point A. All right. On this particular slide, what we're going to be doing is we're going to be matching functions to their derivatives. So this will help you understand like what the features on the original graph say about the derivative and what those look like on the derivative. So a couple of things to think about. One, when does the original function have maxes or mins or horizontal tangents? And also when the original graph is increasing or decreasing. So when the original graph is increasing, the derivative is going to be positive. And when the original graph is decreasing, the derivative is going to be negative. And any place you have a maximum or minimum value where it changes from increasing to decreasing or decreasing to increasing, that means the derivative is going to be 0 at those places. And it's going to cross the x-axis. Now, there could be a place where the derivative is 0 and it doesn't change from being positive to negative or negative to positive. And that would be a place on the original graph where you would have a horizontal tangent, but it would stay increasing or stay decreasing. So we do actually have an example of one of those in this particular set of graphs, and that's graph number 9 right here. So number 9 is always increasing, but it does actually kind of go flat there in the middle. So if we're looking at the derivative here, this derivative is going to be positive all of the time, except here at 0, it's going to touch the x-axis just there, and then it's going to keep increasing after that. So the one that matches up best with this is going to be graph P. So graph 9 is actually going to match up with graph P. Now, if you look at P, P is always positive, okay? So it's always above the x-axis. But here at 0, you see how it touches 0 and then it keeps increasing. So that means the slope is positive the whole time. It goes to 0 for a second and then it goes back positive again. So we have a positive slope here all the way to 0, and then we have positive slopes after that. So graph 9 would match up with graph P. Now, the other thing I want you to pay attention to is all of the quadratic functions. So we have 3 different quadratic functions. We have graph 5, we have graph 13, and we have graph 14. Now, since these are quadratic graphs, their derivatives are actually going to be linear. So 5, 13, and 14 are all going to be linear functions because the derivative of a quadratic function is going to be a linear function. Now, we have to pay attention to how these are different. So graph 5 decreases, and then at 0, it increases. So this one should be negative before 0 and positive after 0. And that looks like this graph right here. So it's negative all the way to 0, and then it turns positive. Okay, which means it's decreasing all the way to 0, and then it turns to increasing. So graph 5 is going to match up with the derivative I. Now let's look at 13. So graph 13 13 is going to be increasing, and then at 0, where x is 0, it turns to decreasing. So this one's going to be positive, and then it's going to change negative. So here it's positive, then it changes negative. So here we have positive slope, here we have a negative slope. So 13 is actually going to match up with L. And then 14, this one is negative and then positive, but its change doesn't happen at 0. Its change happens right here, which correlates to this value where it's got a slope of 0 or a horizontal tangent there. So that one would match up with graph M. So 14 matches up with graph M. All right, now we have two linear functions, graph 7 and graph 18. A linear function has a derivative that is a constant. 7 has a negative slope, so it's going to have a negative constant, so it's going to match up with B. And then 18 has a positive slope, so it's going to match up with A. So 7 is matching up with B, and 18 is matching up with A. Now, 8 is an absolute value, which means it's going to have a negative slope and then a positive slope. So this one's going to look like a piecewise function. So 8 is actually going to match up with D because it has a negative slope and then it has a positive slope. So 8 is going to match up with D. So those are kind of the more obvious ones, okay? So those are a little bit easier to navigate through. All right, so let's go ahead and look at some of the other graphs. So if I look at 17, 17 actually has a vertical tangent at 0, okay? Which means that's going to be a place on the derivative where it's also going to have a vertical tangent because the derivative's not going to exist there. Now, it has a positive slope on this side, and it has a negative slope on this side. So when I look at the derivative, I'm looking for a derivative that is positive on the left and negative on the right, and also has that vertical tangent there. So 17 actually matches up best with the derivative of n because the derivative is positive on the left side here and negative on the right side, and it does not exist there at 0. So 17 is going to be paired up with n. Let's see. Here's another one that has a asymptote. So number 20 does. But number 20 is decreasing and still decreasing. So this one's going to be negative the whole time. So you're looking for a derivative that's always going to be below the x-axis. This one's negative here and negative here. So 20 is going to match up with C. Um, 16 is an exponential. And you know the exponentials, the derivatives are the same. So 16 is an exponential graph, which means its derivative is going to pretty much look exactly the same. So 16 is going to be E. All right, so now we're left with just a few other functions. I want to look at 10 and 19 because 10 and 19 both only exist after 0. So their domains are only 0 and on. Number 19 looks like it has a positive slope, and number 10 looks like it has a negative slope, or it's decreasing. This one's decreasing, this one's increasing. So when I look at the derivatives, I'm looking at K and O, but K is positive and O is negative. So K is actually going to match up with 19 because it has a positive slope. And 10 is going to match up with O because it is negative. All right, so now we're down to 4 more graphs. So number 6, graph 6, is increasing, then it goes to 0 at this maximum point. Then it's decreasing, then it goes to 0 at this minimum point, and then it's increasing. So for this one, we're looking at a graph that is negative, and then positive kind of in the middle there. And then, a graph that's positive negative in the middle, and then positive after. And it crosses the x-axis here and here. So when I look at my options, I'm leaning towards G because G is positive here, which means it's increasing here. It's negative kind of in the middle there, which is negative where this one was decreasing there in the middle. And then it's positive here after. So this one would be positive here after. So I'm matching up 6 with G. Now, if I look at 11, 11 is negative, or decreasing, sorry, which means the first derivative would be negative, and then it's increasing, so it's going to be positive after here. And then we have a place here in the middle where we're at 0 for a minute. So this one starts negative, it's at 0 for a little bit, and then it goes positive. So I am leaning towards H for this one because it's negative, it goes 0 in the middle for a little bit, and then it turns positive. So 11 is going to be matched up with H. So we have 2 more left. Number 12. So number 12 has several mins and maxes. It actually has 3 of them. So that means the derivative is actually going to cross the x-axis 3 times. And that looks like F would be that one. So this one starts off decreasing, which means it starts off negative. It goes increasing for a minute here. So it goes positive. Then it goes decreasing again. So it goes negative. And then it goes increasing again. So it turns positive. So 12 is going to match up with F. Which leaves 15 to be J. So 15 is going to be J. And let's just check it to make sure. So this one would have a vertical or a horizontal tangent here at the top. Which means it would cross 0 here, and it does. And then this one would actually have vertical tangents here and here, and you can see that we're getting kind of close to like an asymptote here and here. So that makes sense to me. This one's also positive and then negative, so it's positive above and then negative below. So 15 is going to match up with J as our last one. So when you're looking at the original function and the derivative, really pay attention to places on the original function where the original function is increasing. That means the derivative is going to be positive. Where the original function is decreasing, the derivative is going to be negative. And where the original function has maxes or mins, that's where the derivative is going to be 0. Okay, so those are what you're looking at when you're trying to compare a function into its graph, derivative graph. Okay, so hopefully kind of matching those up helped you kind of understand that relationship a little bit better. All right, these last few examples are just going to be tying in to what we've learned about critical values, increasing and decreasing with first derivatives, and concavity with second derivatives, to implicit relationships. So when we were doing derivatives, we did regular derivatives where you had all x's like as part of the function. But then we had other functions, or not functions, like relations that had x's and y's in them. So we had to take the derivative with respect to x. So we were doing like that dy dx stuff. So when you have implicit relationships, they're going to follow the same rules. So if dy dx is equal to 0 or dy dx does not exist at a point, then the point is a critical point. If the second derivative is greater than 0 at a point, then the graph is concave up at that point, and then vice versa. If the second derivative is less than 0, then the graph is going to be concave down at that point. So the same rules that apply to regular derivatives, where you just have x's or you just have one variable in them, they also apply to implicitly defined derivatives, where you have x's and y's in them. So the same rules that apply to just like the derivatives with x's, they also apply to the derivatives with x and y's. So let's look at a few examples. I have 3 examples that we're going to look through that use implicit relationships. And we're going to look at how these rules apply to them. So in example 5, it says, consider the curve 3x to the third plus 3 equals ln of 4y squared in the xy plane. At the point -1, 1/2, is the curve increasing or decreasing? Okay, so if it's increasing, the first derivative is going to be positive. if it's increasing, and f prime of x is going to be less than 0 if it's decreasing. So the first thing we have to find is we need to find the derivative of this, and then we can plug in the point and see whether it's positive or negative, and then we can tell if the curve is increasing or decreasing. So let's go ahead and work on finding the derivative of this with respect to x. So we're going to have 9x squared times dy over dx. Oops, no, I don't have to times dy over dx because that was an x. Hang on just a second, y'all. Here we go. Okay. All right, so let's try this again. So we're going to find the derivative with respect to x. So I only have to use dy dx when I find the derivative of a term that has a y in it. All right, so let's start off with 3 times 3. So we got 9x squared. And then the 3 here is going to go away. Then I'm going to have 1 over 4y squared times 8y times dy over dx. I'm going to simplify this down a little bit. So I have 9x squared equals 8y over 4y squared times dy over dx. And then I can simplify down even more. So 9x squared equals 8 over 4 becomes 2. I can also cancel out a y on the top and a y on the bottom. So I end up with 2 over y times dy over dx. And then if I flip around the 2 over y and multiply it on both sides, I'm going to get 9x squared y over 2 equals dy over dx. Okay, and again, I just flipped this over and multiplied it on this side. All right, so here is my derivative. So now I'm going to take my point. I'm going to plug -1 in for x, and I'm going to plug 1/2 in for y. So I'm going to have 9 times -1 squared times 1/2 over 2. Now, I'm not really interested in the actual value of this. I'm just interested in if it's positive or negative. I know that when I square -1, it's going to turn positive. So it really doesn't matter what anything else is. I know that dy dx is going to be positive. So dy over dx is going to be greater than 0, which means our function is going to be increasing. So I really just had to check the sign of it at that place and not really think about anything else. So I know it's going to be increasing at that particular point. Example 5, same curve. No, not the same curve. Sorry, it took a minute to switch. So example 6, consider the curve x squared minus 3 equals e to the y in the xy plane. At the point -2, 0 is the curve concave up or concave down. So concave up and down, we're looking at the second derivative. So I actually need to find the derivative of this thing twice. So let's go ahead and find the derivative, the first derivative, and then I'll work on finding the second derivative after that. So I'm going to go ahead and find the first derivative. So I'll have 2x. The 3 is going to go away, and then I'm going to have e to the y times dy over dx, which means dy over dx is going to equal 2x over e to the y. Now I'm going to find the second derivative. I think I'm going to rewrite this first. So I'm going to change this to 2x times e to the -y. And then I'm going to work on finding the second derivative. So d 2y over dx squared is going to equal 2 e to the -y plus 2x times e to the -y times -1 times dy over dx. Now, I'm going to have to do a little bit of work to simplify this down or to see whether this thing's going to be positive or negative. So I am going to go ahead and change the way this looks a little bit. And then I'm also going to go ahead and substitute this back in for this right here. So I'm going to have d2y over dx2 equals 2 over e to the y. So I just move this back down. Plus, well, actually, I'll do minus. Well, it's going to take forever to try to erase that plus sign. Let's see. Erase. There we go. Okay, finally went away. All right, so right here, I'm going to have this negative 1. Come on, change back, please. So this negative 1 and this positive 2 is going to become negative 2. The x will stay up top. The e to the y is going to come to the bottom. And then I'm going to replace this with this. So times 2x over e to the y. So now let's think about if I plug in this right here, will I get a positive second derivative or a negative second derivative? So if I plug in negative 2 for x and 0 for y, if I plug in 0 for y right here, this is just going to be 2 because e to the 0 is just 1. If I plug in negative 2 right here, so I'm going to plug in negative 2 right here and negative 2 right here. So I already have a negative, and then I'm going to have 2 times negative 2, so that'll be negative 4. Another 2 times negative 2, which will be another negative 4. So I have 3 negatives. So it's actually going to be negative 16 over, and then both of these are going to be 0. So it'll just be over 1. So it'll be 2 minus 16, which is going to be negative 14. So my second derivative is negative. So d2y over dx squared is going to be less than 0. So it's going to be concave down. All right, and now I have my last example, which is example 7. It says, consider the curve y to the third minus y equals x squared on the xy plane. It is known that dy over dx equals 2x over 3y squared minus 1, and d squared y over d, or d2y over dx2 equals 2 over 3y squared minus 1 minus 24x squared y over 3y squared minus 1 all squared. At the point 0, 1 on the curve, is the point a relative max, relative min, or neither? So if it's going to be a relative max or a relative min, okay, so if it's a relative max or a relative min, the first derivative must be equal to 0. And then if it's a max, the second derivative has to be concave down, so it needs to be less than 0. And if it's a min, the second derivative has to be greater than 0, because max is opening down and min is opening up. So first, let's check the first derivative and see if we get 0. Because if we don't get 0, then we know it's not going to be either one of those. So let's go ahead and check the first derivative. So we're going to think about plugging in 0 and 1 into this derivative right here. So if I plug 0 into the top, into x, I do get 0. So I get 0 on top. Now let's see what we get on the bottom. So we get 3 times 1 squared, which is 3 minus 1, which is 2. So yes, dy over dx does equal 0. So it could be a max or a min. So now we need to check it in the second derivative. So I'm going to go to the second derivative here, and I'm trying to figure out whether it's positive or negative. So when I plug in 1 for this y value, I'm going to have 3 times 1 minus 1, which is positive. So that first term is going to be positive 2 over positive 2. So d2y over dx2. if I plug into that first one, I'm going to get 2 over 2 because I'm plugging in x for 0 and y for 1. And then in the second one, I'm going to have minus 24 times 0 squared times y. It really doesn't matter what y is. That top's going to be 0. And then the bottom is going to be 2 squared. But it's overall it's just going to be 0. So that's 0. So this is positive 1. So it's going to be positive, which means it's going to be a minimum. So it is a relative minimum. What in the world? All right, so we have a relative min. Come on. My iPad's getting tired of making videos. Okay, so relative min at 0, 1. And that's because dy dx equals 0 and d2y over dx2 is greater than 0, which means it's going to be a relative minimum.